In this video, we're going to be taking a look at the derivative as a rate of change. When we think of the derivative as a rate of change, we generally think of situations where there are units attached to the variables involved in the application. This mostly means modeling real-world situations, such as change in population or a change in profit or change in cost of producing some particular item. When we think about the rate of change, we're thinking about how one variable changes in relationship to another, such as velocity or acceleration. Velocity is often given in miles per hour, meaning the rate of change of the miles, the position, with respect to time, the hour. We're going to be taking a look at quite a few applications, and we'll get to use the rules that we learned in the last section. I'll share my screen with you so we can get started. Here are the learning objectives for this section. We're going to determine a new value of a quantity from the old value and the amount of change. In other words, going to approximate the new change of a quantity given the original amount and the rate of change of the situation. Then we're going to calculate the average rate of change, which we've done many times before, as the slope of the secant line. And of course, then we'll compute the instantaneous rate of change, which is the slope of the tangent line. In other words, the derivative. We'll apply these rates of change to displacement, velocity, and acceleration of an object moving in a straight line. This will probably be the most difficult part of this section, learning to interpret a position time graph with respect to velocity, acceleration, location of the position, and whether it is speeding up or slowing down, which is not the same thing as acceleration and deceleration. We'll also predict the future population of some particular city or perhaps a colony of bacteria from the amount originally present and the population growth rate. We'll also use derivatives to find what's called the marginal cost, marginal revenue, or marginal profit. Marginal cost is the idea of, well, if I've already produced 10 items, what would be the cost of producing the 11th? Or if I've sold 10 items, what's the revenue that I can expect from the sale of the 11th? And the same for profit. Let's go ahead and get into it now by taking a look at the amount of change formula. In the amount of change formula, we're actually pulling apart a little bit the slope of the secant line formula. That is the difference quotient. It's not going away for some time to come. If we take a function defined over an interval between some particular value, say 10, and scoot over a little bit, 10 plus a little bit, or maybe minus a little bit, it could be on either side, h could be positive or negative, then the amount of change of the function over the interval is just the change in the y values between f of a and f of a plus h. We can write f of a plus h minus f of a to represent this change in y value. It could be positive, it could be negative. We want again to emphasize that the average rate of change is the slope of the secant line given by the difference quotient that you see here. And the instantaneous rate of change, which you see here, is given by the limit of the difference quotient as the distance between the 2 points gets smaller and smaller. Instantaneous means 0 time has elapsed, and this is why we need the limit. We want to now approximate the value of the function later in time, the f of a plus h, by taking a very small interval. That is, we're going to have h be a tiny amount, not 1, not 2, but 0.1 or 0.01. very small. If the value of h is very, very small, then I can approximate the average rate of change with the instantaneous and vice versa. In this case, I want to approximate the instantaneous rate of change at A with the slope of the secant line when the points are very close together. For example, what's the change in your velocity on a freeway over 1 second? Probably not very much. Now we can take this formula and we can manipulate it. Since these are approximately equal when h is very small, we can solve for f of a plus h by multiplying both sides by h to obtain h times f prime at a approximately equal to f of a plus h minus f of a. Then we isolate f of a plus h by adding f of a to both sides of the equation. Note that these are only approximately equal. This gives us an approximation of what the new value of the function is going to be. And this will work provided that h is very small. We're using the y value on the tangent line to approximate the y value on the actual function. As long as h is small, then the tangent line should still be close to the graph of the function. We'll do this again later this semester when we're studying integrals. Let's look at a graph and see what the error is in using the point on the tangent line to approximate the point on the graph. Here's our point A, f of A, and we've zoomed in this graph, so the distance between A and A plus H may only be 0.1 or less. When we're looking at this becomes the point A plus H, f of A plus H, which is on the blue graph. Now we want to approximate that by taking the point that's on the tangent line to the graph at the point A. When we do that, we're using the same x-coordinate, A plus H, but we're using our approximation, which is actually on the tangent line here in orange. When you do this, you can see that those y values are not exactly the same. They're a little bit apart. As long as we take an h value that makes our point be relatively close to A, f of A, then the tangent line will still be relatively close to the curve. And this error that you see here should not be terribly large. This is the error in using that approximation, f of A plus h times f prime of A, to estimate the value on the curve itself. Now let's take a look at an example. In this particular example, what we want to look at is a function where f of 10 is -5, and the derivative at 10, same value, is 6. We want to estimate what the function value is at 10.1. But we're not given the function. In this case, we can use that tangent line approximation to approximate the value on the function. In this case, we want to find f of 10.1, which of course is 10 plus 0.1, our A plus H. And we want to approximate this with f of 10, f of A, plus h times f prime of A, which would give us 0.1 times the derivative at 10. Working this out, we have an approximation of -5 plus 0.1 times 6. This is going to come out to be a -4.4. We're approximating the true value on the function for f of 10.1 with the value on the tangent line, which is negative 4.4. We'll use this formula later on in some application problems. We don't typically do this when we don't have an application in order to apply it to. Let's now take a look at motion along the line. Motion along a line is also called rectilinear motion. I don't know why exactly, but that's what it's called. Now, what does this mean? This means like you're traveling on an interstate that goes north and south. We'll assume that it doesn't veer out of the way and have any curves. It's a straight shot, north-south. Or it could be like I-70 and travel east-west. And again, we're going to assume it doesn't take any curves. We're going to assume it's a straight line going east-west. What we want to do is we want to look at the position time graph and predict and say where the velocity is positive, where it is negative, where it is accelerating, where it is decelerating, which is not the same as where it's speeding up or slowing down. We're also going to want to know where it is in position with respect to the origin, which in our case might be a city. The city would represent being a sort of starting place. So are you east of Denver or are you west of Denver? How do we know whether we're on the east side of Denver or the west side by looking at the position time graph? Here are the definitions that we'll be using as we do this. Remember that the derivative of position time is the velocity, and the derivative of the velocity is the acceleration. And in fact, the derivative of acceleration is the jerk, that forward or back motion you feel when the deceleration or acceleration is applied. When we look at these, we're allowing s of t to be our position time function. So velocity is s prime, speed is the magnitude of velocity. It does not have a direction. Velocity is a vector. It has both direction and magnitude. I'm traveling 70 miles per hour west. 70 miles per hour is my speed, but west is my direction. The two together give you the vector velocity. Acceleration would be s double prime or v prime for velocity. What we want to talk about now is a particle moving along a coordinate axis. We're going to assume that this particle is actually a car and that it's traveling along this straight road, moving left to right. We'll assume that Denver is our origin or starting place, and it's on I-70, and it is traveling either east or west. So when we look at the graph, we want to describe the motion of the car as it relates to the graph. Now, the car is not following this path. The car is on the interstate traveling either east or west, back and forth on a straight line, rectilinear motion. How can we describe where it is in relation to Denver? Denver is going to be, in essence, the x-axis. Denver is our starting point. If the position has a y-coordinate of 0, it's in the heart of Denver. If the graph is shown above the x-axis, it must be on the positive side of Denver. As we look at our graph here, we're going to call this direction east or right, and we're going to call this direction west or left. If the position is above the x-axis, it is to the east or right of Denver. If the position is below the x-axis, it is to the left or west of Denver. Notice that time cannot be negative, so there is no graph to the left of the y-axis. It doesn't make any sense to allow time to be negative. Now let's take a look at this graph and describe the position as we see it. It starts out definitely on the right side of Denver, right side of the starting place, or to the east. Then it must be traveling to the west because later in time goes across the horizontal, it becomes on the left side of Denver or to the west. Then at some point it must turn around and start heading back east. It's still in this section on the west side of Denver because it's below the x-axis, but it must be headed back east because here, from close to 5 out, it's back again on the east or right side of Denver. We can also tell that this particle is already moving at t equals 0 because the slope of the tangent line at the point 0, 1 is not 0. This car did not start from rest. Now, we also can predict that it's actually traveling. Well, let me scroll back up to this one. It's actually traveling in the west direction. Now, how do I know it's headed to the left or west of Denver? The slope of the tangent line is negative. The slope of the tangent line is negative, the velocity is negative, which must mean that it's headed out to the west. But notice right here at this point, we're going to have at one instant right there at looks like 2.5, we're going to have a horizontal tangent line. The car must stop at that point. And then it must be turned around because on the right side of that point, the tangent line becomes positively sloped. If the tangent line is positively sloped, the velocity is positive. When velocity is positive, it is moving to the right, or in our case, east. So in this case, we can say that positive velocity means that it's traveling towards the right. If it were traveling on a north-south road, it would be traveling north or up, right or east. If we have negative velocity, then this implies that it must be traveling towards the left or west. If we have 0 velocity, it is stopped. So let's put together some of the information that we've talked about thus far. We've written down what it means to have positive and negative velocity and 0 velocity. Let's make note of what it means to be above the x-axis or t-axis and below the t-axis. If we are above the t-axis, then we are located right of the origin, or let's not use origin, let's use starting point. In our case, we called it the heart of Denver. If you are below the t-axis, then you must be located to the left of the starting point, or Denver. That doesn't mean you're headed left. or headed right. You can be west of Denver and be headed east or west or north or south, but our car is moving along a straight line. What if you are on the t-axis? Then you are located at the starting point, which in our case is in the heart of Denver. All right, let's now take a look at another part of this particular situation, and let's talk about whether the car is speeding up, slowing down, accelerating, or decelerating. Now, when we're looking at the graph, we have a vertex in the graph at about 2.5, negative 5.25. This means that it's located basically 5.25 perhaps miles to the left of the heart of Denver. And that's occurring when the time is 2.5, I don't know, whatever the units are, minutes. When we're looking at this, I know that the vehicle is stopped right there at 2.5 because I have a horizontal tangent line. V equals 0, it is stopped. Well, think about this. If you are moving because your tangent line is not 0 and you're headed left or west because the tangent line has a negative slope, but then you stop, don't you have to be slowing down? Yes, you do. We're going to use SD to represent slowing down. We're going to use SU to represent speeding up. On the left side of either a minimum or a maximum on a graph, it must be slowing down just to the left of either a maximum or a minimum. So it must be slowing down on this section here. It's moving, but it's going to come to a stop, so it has to be slowing down. What about just to the right side of that minimum point? Just to the right side, the tangent line is no longer horizontal, so the car is moving. First, it starts out relatively low in magnitude, and then it increases. The car must be, you got it, speeding up. Now, we want to talk a little bit about what acceleration means. Before we do that, let's make note of what speeding up and slowing down mean. Slowing down just to the left of maximums and minimums. We're speeding up just to the right of maximums and minimums. There is a point where it stops speeding up and starts slowing down, and we'll take a look at that in another graph in just a moment. This particular graph here has only the slowing down to 0 and the speeding up. It doesn't have one where it is speeding up and then slowing down without going through 0. When we look at this graph and we want to talk about acceleration, notice that the graph is cupped up. Remember that we call this curvature of the graph concavity. When it is cupped up like a cup, we say it is concave up. When it is curved down, we say it is down like a frown. In this case, this curve is always concave up. This gives you a way to remember which one is which. The concavity is actually telling you about the acceleration. When we look at this, notice that it is concave up everywhere, which means that this particular graph, the acceleration is always positive. Now, you may go, what? How is that possible? At one point, it's slowing down, the velocity is negative, and then the velocity is positive. There's a point here where the vehicle is stopped. How can the acceleration be positive at all points? Remember that acceleration is the rate of change of the velocity. If we throw some numbers out here, it will help you to realize that the rate of change of velocity with respect to time is always strictly positive. At the points here on the graph, as we move across like this, we're getting velocities something like this, negative 70 miles per hour, negative 60 miles per hour, negative 40 miles per hour, negative 15 miles per hour, 0, then 15, then maybe 30, then 40, then 60. If I want to find the rate of change, notice that this is in terms of increasing time. This is going to be my velocity, and my time is maybe 0, 1, 2, 3, 4, 5, etc. That's not actually what the times are because we know it's stopped at 2.5. But for ease of calculation, we'll use these values here. What is the rate of change? It's going to be the change in the y values divided by the change in the time values. That's going to give me, for example, negative 60 minus a negative 70 divided by the positive time interval 1 minus 0. If I always take the one after minus the one in front, the time in the denominator will always be positive. Notice that this double negative is going to result in a positive 70, which means I have a positive rate of change of velocity of 10 miles per minute. That means that the acceleration is positive. In fact, even at 0, it was negative, then 0, then positive. So the velocity is increasing in value, since going from a negative to 0 to positive means it's getting more positive, increasing. And that means the acceleration is going to be positive as well. Do not think of speeding up and slowing down as acceleration and deceleration. They're related, but they are not the same in the physics sense. Since we've called a concave up positive acceleration, you may guess that concave down means negative acceleration, and it does. And where those 2 points fit together, from concave up to concave down, called an inflection point, that's where the acceleration is 0. In that case, you can imagine taking your foot off the gas, but not yet applying the brake. You're coasting. You do not have a rate of change of velocity, so acceleration is 0. Now, let's take a look at another one. We want to look at this graph that I'm going to scroll up in just a moment, because we want to have a graph where we do have a change in curvature. Our last graph was concave up everywhere, meaning acceleration was always going to be positive. The point where the graph turns and stops being cupped up to being cupped down, or vice versa, is called an inflection point. An inflection point is where the acceleration is zero and the car or the particle is neither accelerating nor decelerating. In a sense, it's coasting. Let's take a look at this graph right here. Notice that they've written down when the velocity is positive and negative, and also when the acceleration is positive and negative. On this section, up to the value of A, the graph is cupped up like a cup, concave up, which means it must have positive acceleration. So F double prime is greater than zero in both cases. However, the velocity is changing. Notice that from the beginning over to this point with the dashed teal line, the slope with a tangent line is negative, which means the velocity, the first derivative, is negative. Then the vehicle stops for one moment, although the acceleration is still positive. And then it begins moving again, slowing down here, speeding up here. Over here, the acceleration is still positive, and the tangent line is also positive, sloped up. Notice what happens at the inflection point. At the inflection point, watch my hand as it moves across and tell me what's happening to the slant of the tangent line right at the inflection point. You got it. The inflection point is where the tangent line is the steepest, whether it's uphill or downhill. That point where it changes concavity is where the derivative reaches its maximum or minimum, as we saw earlier when we drew the graph of the derivative from the function. It also means on a position time graph that the acceleration there is zero. It's also the point where the vehicle or particle stops speeding up and starts slowing down, or stops slowing down and starts speeding up, depending on the shape of the graph. Right here, it is going to be speeding up. Let me color code the sections. It's speeding up here, and it's slowing down here. Oops, not so good. Notice that it has to be slowing down here because it's about to stop. Right here, V equals zero, and V equals zero here. Then it gets moving again because the tangent line's no longer horizontal. The velocity must be negative, but it must be, in fact, speeding up because it was stopped. So here we must have another yellow section. Notice that on this half of the graph, to the right of the inflection point, the acceleration, F double prime, is negative, indicating that it's actually decelerating. When we look at these, we can combine the signs of the first and second derivative to predict whether the car is speeding up or slowing down. If the velocity is negative, but the acceleration is positive, it must be a combination of positive and negative, which means it's slowing down. If the velocity is positive and the acceleration is positive, a positive and positive make positive, the car must be speeding up. Again, if the first derivative is positive, but the second is negative, we have a positive and a negative, so the vehicle is slowing down. If they're both negative, two negatives make a positive, the vehicle is speeding up. All right, we're now ready to go ahead and take a look at some examples. We're going to be looking at these examples and giving the information about where the vehicle or particle is located, whether it is left of the beginning place or to the right of it, and whether it is at the beginning place, whether it is headed left, headed right, whether it is stopped or has positive or negative velocity, and whether it is moving left, moving right, and whether or not the acceleration is positive or negative. Basically, everything. Let's now look at the first graph. Let's kind of go through a little bit and think about what this means. Remember, we know from drawing the derivative of a function from the graph of the function that in this horizontal line segment region, we know the derivative is 0. This represents position versus time, so this represents velocity being 0. Here, the tangent line is positive up to the maximum, so the velocity is positive, but it's concave down, so the acceleration is negative. Combination of a positive and negative must mean it's slowing down. Let's now turn our attention to the questions and answer each one at a time. Use the graph of the position function to determine the time intervals when the object is to the left of the starting place, the heart of Denver, or to the right of the starting place. When I look at this graph, there's one moment when it's actually at the starting place, which is at time equals 0. The rest of the time, the entire graph is above the t-axis, and that means that it is always to the right, or in our case, what we would call east. Always, oops, wrong color. Always right. It's at the beginning place when t equals 0 only. Now let's talk about when the velocity is positive, negative, or 0. And we'll have to estimate the intervals over which this happens. The tangent line is positive till I reach this maximum. And this maximum looks like it's about at 1.5. So the velocity is positive over the interval from 0 to 1.5. And you can either leave the two ends of the interval open or closed. I don't have a preference, but probably the homework system will want them open. When we look at another region, the next one over, notice that the tangent line is sloped negatively. So between 1.5 and 2, it has negative velocity. At 2, the vehicle stops. This means that the velocity is 0. So from 2 out to 5, the vehicle is not moving. When the vehicle begins moving again, but it has negative velocity, meaning it must be headed to the left. It's still on the right side of Denver, but it's headed west. This means it has negative velocity between 5 and 6 again. And then it stops for one instant at 6. So it's stopped at 6 and 0 there. And it begins moving again towards the right with positive velocity. And so we would say between 6 and 7, it's moving again. Remember to use the letter U between your symbols. And if you have a single point, you put it inside curved braces. Let's now talk about when the object is moving left, moving right, or stopped. Moving left means negative velocity. So that would be here. Moving to the right means positive velocity, and that would be here. Stopped means velocity is 0. Now we want to sketch the graph of the velocity function. And remember that the velocity function is the derivative of the position function. And that means basically you're going to draw the derivative. I know it starts out steep and positive, and then it decreases until it reaches 1.5. At 1.5, the derivative is 0. Then it becomes a little negative till 2, where it's stopped. But there's a corner here in the graph, which means the derivative does not exist, so I make it an empty hole. Then I have a section between 2 and 5 where the vehicle is stopped, so the graph of the velocity function is going to be on the t-axis, a horizontal segment on the t-axis. Velocity is 0. Then it gets moving again, but with negative velocity. This starts out at a large magnitude for steepness, but negative, and decreases until, or increases actually, till it reaches 0. So it's down here somewhere and comes up until it hits 6, where it is 0. Then it changes and heads the other direction with a positive velocity. Your graph of the derivative should look something more or less similar to that. Now let's use the graph of the velocity function and the concavity to say where it is, acceleration is positive, negative, or 0. Remember, acceleration is the first derivative of the velocity and the second derivative of the position. Where is it positive? Where is it negative? Where is it 0? This first section from 0 to 1.5, it's definitely concave down, which means it's negative. This section here, the velocity is 0 over the entire interval. And when we graph this, it looks like this horizontal line segment here. Because acceleration is the first derivative of velocity, if I were to draw the derivative of this horizontal section, it would again be a horizontal section, which means that the acceleration over this extended interval from 2 to 5 is 0 acceleration. Now I have a region where the graph is puffed up, which means that it is concave up and I have positive acceleration. I would call this between 5 and 7. Missed anything. Oh, I did miss one thing. I looked only at the section up to the maximum, but between the maximum and 2, it's also concave down. So you can either connect them, or you could just go ahead and write this as 0 to 2. And again, we can either include the endpoints or leave the endpoints out. Most likely, the textbook and the homework system want open parentheses. When is the object speeding up or slowing down? That requires us to take the combination of signs between the first and the second derivative, or to simply look at the graph and predict based on the location of the maximums and minimums. On the left side of a maximum or minimum, it must be slowing down. That's because velocity is positive, but acceleration is negative. So I would say that it is slowing down between 0 and 1.5. When I get between 1.5 and 2, though, both the velocity and acceleration are negative, so it must be speeding up. On the section where it's not moving, it's neither speeding up nor slowing down. It's not moving. What about on this section here between 5 and 6? It is moving because the slope of the tangent line is not 0, but it is on the left side of a minimum. There's no inflection point, which means that it must be slowing down over the entire region between 5 and 6. And then on the right side, there's again no inflection point where the speeding up, slowing down behavior changes and acceleration changes. So we must have that it is speeding up over this section from 6 to 7. Now I want you to practice this on your own. The questions are the same as what we've done before, but this is our new graph that you see here. In this particular graph, some tangent lines are drawn to indicate what it looks like. Notice here between 5 and 6 that the tangent line is horizontal. That section is a horizontal line. Pause the video, work it out, turn the video back on, and we'll compare our results. So let's see what we have. Because the graph of the position versus time graph is always above the t-axis, it's always to the right. It never hits the t-axis, so it is never at that central location, what we've been referring to as Denver. When we talk about the velocity, we're looking for a positively sloped tangent line, which occurs between 0 and 1, and again between 3 and about 5. That also means that the particle or the car is moving to the right. Now, when is the velocity negative? Between 1 and 3, and that's it. That's the only time the car or particle is moving left. When is it 0? It's 0 here at 1, and again at 3, and over the interval from 5 out to 6, indicating that at those locations and over the time interval from 5 to 6, the car is actually stopped. Now we want to talk about the graph of the velocity function. We can tell in this region here that we have positive velocity, but it's getting lower in value as it approaches the maximum where it is 0. So it comes down in a near linear section. We have a change in concavity here at about 2, where it changes from being concave down to being concave up. This inflection point is going to change whether it is speeding up and slowing down or accelerating or decelerating. When we draw the graph of the derivative, the inflection point becomes either a minimum or a maximum. In this case, a minimum. When we look at the next location, we see that we have a minimum in the original graph at 3, which means again that it is approaching 0. Here, however, the velocity is negative all the way between 1 and 3, which means that entire section is below the t-axis, with a minimum at 2, where the inflection point occurred. The next one is kind of hard to pinpoint. I called it about 4.5. I would take anything relatively close, with relative being, well, you could be up to 0.5 off. There has to be an inflection point in this region between 3 and 5, because in this tiny little section just to the left of 5, it's clearly concave down. That means there has to be an inflection point. Again, the tangent line is sloped positively in both sections, but this inflection point will relate to either a maximum or a minimum in the graph. Because it was positive and reached maximum steepness at the inflection point, it becomes a maximum. Then it drops very rapidly to approach zero over the last section. The next thing we want to determine is the acceleration and the speeding up and slowing down. Go ahead and compare your values to mine by pausing the video if you'd like. When we look at this, it's concave up between that 2 and 4.5 section. It's concave down between 0 and 2, and again from about 4.5 to 5. We have an inflection point where the acceleration is 0 at 2 instants in time, 2 and 4.5, and over the extended time interval from 5 to 6. It's speeding up between 1 and 2 and 3 and about 4.5. And it's slowing down between 0, 1, 2 to 3, and again from 4.5 to 5. When we look at the graph, to the left of a place where it has 0 velocity, it must be slowing down. Notice that the slowing down occurs between the inflection point and the minimum on the graph. Again, between the inflection point and this 0 section, we must have the vehicle slowing down. Between the place where it stopped and where it reaches maximum velocity in an absolute value sense, it must be speeding up. Here, to the right of this maximum, it must be speeding up, but headed left in the negative direction. Let's take a look at example 5 together, or 4. In example 4, we have a graph of the position time function, which has our x of t, which in this case represents the position with respect to time. We want to know which of these graphs represents the same motion, but these graphs are the velocity function, the derivative of position. Well, let's think about what has to happen on the derivative. This little section is horizontal, which means the velocity is 0. So that section should correspond to a horizontal segment on the t-axis. Well, what does that leave out? Which of these does that eliminate? Definitely eliminates A, B, and D. They do have horizontal segments, but not indicating 0 velocity. It's not on the t-axis. So we can mark out these 3 graphs, leaving only C and E. Now let's look at the next segment. This is a linear section, but it is slanted positively, which must mean we have a positive velocity, but it's not changing, it's constant. This will correspond to a horizontal segment above the t-axis in the velocity. This should be the graph C. We can see here it's a horizontal section, meaning the velocity is constantly the same value, but positive because it's above the t-axis. This part would indicate that it was changing, and because the velocity is not constant, it wouldn't correspond to a linear segment in the graph of the original. E is out. We've eliminated all but C, but let's check to make sure it meets our expectation. The next segment is a long section where it is negatively sloped, but again, it's a line, meaning the velocity is constant, but negative. This will be a horizontal section below the t-axis in the graph of the derivative. And finally, in the graph of the position function, we have a horizontal line segment indicating velocity is 0. So we should have a horizontal line segment in the graph of the derivative. We have 2 more examples to take a look at. And the first one is an applied problem. In this problem, we have a ball thrown downward with a speed of 8 feet per second from the top of a 64-foot tall building. After t seconds, its height above the ground is given by negative 16t squared minus 8t plus 64. Let's draw a picture that represents what we have. We have a building and we have the ground, maybe a tree over here, and we threw the ball down. The ball is falling straight down, and our building is 64 feet tall. S represents the height above the ground. We want to know how long does it take the ball to hit the ground. When the ball hits the ground, its position will be 0. Again, you have to know from what point you are measuring the height. Are you measuring the height from the top of the building or from the ground? It says in the statement of the problem that the height is from the ground up. In this case, we need to find out when S of t equals 0. In other words, what's t when S of t is 0? We set this equation equal to 0 and we solve. Notice that there is a common factor of 8, which we can divide from all 3 parts. I'm going to divide by a -8 so that I can get my highest degree term to have a positive coefficient. This gives me 2t squared plus t minus 8 equals 0. You can try, but this does not factor. And if it doesn't factor, your choice is either completing the square or using the quadratic formula. I'm going to use the quadratic formula with a equal to 2, b equal to 1, and c equal to -8. My time has to be the opposite of b plus or minus the square root of b squared minus 4 times a, which is 2, times c, which is -8, all of which is divided by 2 times the leading coefficient. Let's go ahead and reduce this now. This gives me, why did I write 2 4s? This gives me 2 possibilities. -1 plus the square root of 65, all divided by 4, and -1 minus the square root of 65, all divided by 4. One of these is definitely not the solution. Which one? Yes, it is not possible for time to be negative. So even though it solves the equation, it can't represent the time. It's got to be the -1 plus the square root of 65 divided by 4. This turns out to be about 1.77 seconds, but we are not going to use that value in our equation. I expect your answers to be precise. Do not approximate until the last step. We now know it takes that long for the ball to hit the ground. We want the velocity when it hits the ground. In order to find the velocity, the next part involves taking the derivative. When we take the derivative, we get the velocity function. I want to know what the velocity is at -1 plus square root 65 divided by 4 seconds. That means find the velocity function, v of t, which is equal to s prime of t. This will give me -32t minus 8. Now I'm going to substitute the value that I found into this expression. This would give me that v at -1 plus the square root of 65 divided by 4 seconds would be a velocity of -32 times -1 plus the square root of 65 all divided by 4 minus 8. The -32 cancels with the 4 and I get -8 times -1 plus the square root of 65 minus 8. This is going to give me a negative value for the velocity. When I distribute this, I end up with 8 minus 8 square roots of 65 minus another 8. which gives me negative 8 square roots of 65. Now you may approximate. This gives me roughly negative 64.5, and I believe it was in feet per second. So this would give me the velocity when it hits the ground. At the instant it hits the ground, it's traveling at a speed of negative 64.5 feet per second. Let's now look at example 6. Example 6 is covering a hummingbird flying along a straight line in t seconds, given by the equation 3t cubed minus 7t in meters. We want to find the velocity of the bird at 1 second, the acceleration of the bird at 1 second, and we want to define the acceleration of the bird when the velocity is 0. Remember, unless it's an extended time interval where the velocity is 0, the acceleration may not be 0 just because the velocity is. Let's write down our velocity and acceleration functions. V of t is equal to the derivative of position. This is going to give me 9t squared minus 7. The acceleration is the derivative of velocity and the second derivative of position. And this is going to give me 18t. Now I want to find the velocity of the bird at 1 second. So v of 1 is equal to the derivative of position at 1, which basically gives me, well, 2. And this will be in meters per second, 2 meters per second. Now we want to take a look at the next part, find the acceleration of the bird at 1 second. The acceleration of the bird at 1 second is going to give us the second derivative of position at 1 second, which is 18 times 1, which would end up being 18. It will be in units of meters per second squared. Finally, we want the acceleration of the bird when the velocity is 0. So we take the velocity function, 9t squared minus 7, and we set it equal to 0. When we solve for t, we end up with t squared equal to 7/9, and we take the square root of both sides. Normally, when you're putting in the radical, you'll put in a plus or minus. In this case, we know that the time represents something positive, so it will be strictly the positive root, though mathematically it would be either one. In our case, we get square root of 7 divided by 3. Now to find the acceleration, I find the acceleration at square root of 7 divided by 3. And this is going to give me 18 times root 7 over 3, which is 6 root 7 meters per second squared. Now that we have talked a lot about position and velocity and acceleration, let's take a look at some other situations where the derivative is very useful in describing the rate of change in a particular application problem. We're going to look now at population change. We can use a current population together with the growth rate, the rate of change, to estimate the size of the population in the future. Again, what we're doing is we're using the value on the tangent line to approximate the value on the actual function. This is the equation that we did earlier to represent this new value. When we're looking at population, we'll let P of t represent the number of things in the population, people, maybe bacteria, something like that. It could also be the number of deer that live in a certain forest or area. The population growth or decline is given by the first derivative of population. We can approximate the population by using this rate formula up here, this change formula, which tells us that the new population is roughly equal to the original population plus the small change times the growth rate. Now we want to take a look at example 7, which describes a mosquito colony that is known at the beginning to have 3,000 mosquitoes. That means the population at t equals 0 is 3,000. If the growth rate, the rate of change or first derivative at 0 is 100, can we use this to estimate how many mosquitoes we have in 3 days without the actual function? And the answer is yes. We're going to use our equation here that the derivative is roughly equal to the slope of the secant line as long as the interval is small. In this case, we want to find the population after 3 days. So to find population at 3 days, we're going to take the population at the beginning and we're going to add 3 times the growth rate at the original value. Now, this is going to give me 3,000, my initial value of mosquitoes, plus 3 times the growth rate of 100 mosquitoes per day, which is going to give me that I now have approximately 3,300 mosquitoes. Let's now look at an example that refers to bacteria. In this one, we're given a more complicated formula, and we're actually given the formula. We have 3,000 times the quantity, 1 plus 4t, all divided by t squared plus 100. T is measured in hours. The bacteria are growing, and we want to find the rate of change of the bacteria, the rate of change at the beginning, after 10 hours, after 20 hours, and after 30 hours, the first derivative at those values. And then we want to interpret what's happening with the bacteria based on what we've observed about the growth rate at different hours. First, to find the rate of change, we need to find the derivative. Go ahead and pause the video, work out the derivative, find the derivative value at those different numbers, then turn the video back on and we'll review your results. So let's compare. In this particular problem, I chose to factor out the 3,000 as a common factor. Then I have a sum, and the derivative of a sum is the sum of the derivatives. The derivative of 1 is 0. And that left me with the derivative of the quotient part, which I did using the quotient rule. F of t is 4t, whose derivative is 4, and g of t is t squared plus 100, whose derivative is 2t. When I work it out, I get 3,000 times the ratio of negative 4t squared plus 100 over t squared plus 100 squared. Now I want to take that derivative and I want to compute the rate of change of bacteria with respect to time and hours at the different values 0, 10 hours, 20 hours, and 30 hours. When I substitute 0 in place of t, I have 120 bacteria per hour. In other words, every hour, I'm getting 120 bacteria more at that point in time. On the graph of the derivative, this corresponds to a positive value. Then at 10 hours, when I substitute 10, I end up with 0 in the numerator of the fraction part, meaning that the rate of change of bacteria per hour has gone to 0. Neither adding nor subtracting the bacteria at that point in time. On the graph, this means that I have reached the t-axis. Then at n equal 20, the rate of change is negative 14.4 bacteria per hour. But at n equal or t equal 30, the rate of change is negative 9.6 bacteria per hour. The magnitude between these two is greater at 20 than it is at 30, which means that I must have a low spot in the graph, and then it's coming back up and probably approaching 0. In other words, I start out by adding bacteria. Then the growth rate slows and it becomes 0. Then it begins to decrease, meaning that I have fewer bacteria per hour. I'm losing bacteria. And then the rate at which I lose bacteria slows down, but I continue to lose bacteria. Let's now take a look at another application for rate of change as the derivative. This is going to be in business or economics when we consider cost, revenue, and profit. The concept of a marginal function is very common in business and economics. Again, the marginal cost is the derivative of the cost function. And the marginal revenue is the derivative of the revenue function. The marginal profit is the derivative of the profit function. But because profit is revenue minus cost, that means it's the derivative of the revenue minus the derivative of the cost. Now, what exactly does that mean in terms of what you're doing? If we let C of X represent the cost of producing X items, say 50, the marginal cost, MC of X, is given by the derivative of the cost function. It represents the cost of producing the next item after having already produced X. So the marginal cost of 50 is actually the cost of producing the 51st item. When we look at revenue, the marginal revenue is the derivative of revenue, and it represents the revenue that you receive after selling the next item after having already made X items. If we've already sold 50, then the marginal revenue of 50 is the revenue received from selling the 51st. We have the same idea with profit. When we look at profit, we see that if we've already sold 50, the marginal profit of 50 is the profit received from selling the 51st item. It's also given by the marginal revenue at 50 minus the marginal cost at 50. We can also approximate these values using that approximation formula that we found at the beginning. As long as it's a small interval, then the instantaneous rate of change is roughly equivalent to the average rate of change. The slope on the tangent line is close to the slope of the secant line. For a marginal cost, revenue, or profit situation, a relatively small value would be 1. So we'll let H represent 1. Then we can approximate our marginal cost, the derivative of cost, with the difference quotient representing slope of the secant line, the average cost of X plus 1 minus the cost of X, all divided by 1, the difference between X plus 1 and X. And we get this formula here, that the marginal cost is roughly the difference in the cost between the 51st item and the 50th item. Let's look at a last couple of examples to demonstrate this application of the derivative. Suppose the profit obtained from the sale of X fish fry dinners is given by negative 0.03 x squared plus 8x minus 50. Use the marginal profit function to estimate the profit from the sale of the 101st fish fry dinner. To get the marginal profit of the 101st, we need to find the marginal profit of 100, the one before that. In this case, the marginal profit of 100 is going to be equal to the derivative of the profit function with 100 substituted in. We can find the derivative of the function p of x by taking the derivative of this example that we have. This gives us negative 0.06x plus 8. When we substitute 100 into this equation, we end up with the following value. We end up with $2. The profit on the 101st fish fry dinner is $2. Let's now look at the last example in this video. The cost function in dollars of a company that manufactures food processors is given by 200 plus 7 divided by x plus x squared divided by 7, where x is the number of food processors that are made. We want to find the marginal cost function and then use it to estimate the cost of the 13th food processor. That means we actually need the marginal cost of the 12th, the one before 13. Then we want to find the actual cost of manufacturing the 13th food processor. Let's find the marginal cost function first. In this particular case, we may want to rewrite the cost function in a slightly better form for taking the derivative. I'm going to rewrite 7 divided by x as 7x to the negative 1. I'm going to rewrite x squared divided by 7 as 1/7 x squared. Now I'm going to find the derivative, and that will give me the marginal cost function. In this case, the derivative of 200 is 0. Applying the power rule to the next term, I get negative 7x to the negative 2 plus 2/7 x. This can be rewritten as negative 7 divided by x squared plus 2x divided by 7. Now I want to use that to find the cost of manufacturing the 13th food processor by taking the marginal cost of the 12, the first 12. When I do that, the marginal cost of 12 is going to give me negative 7 divided by 144 plus 24 divided by 7. When you get a common denominator and work this out, it comes out to be, I hope I've written this correctly, $3.38. The cost of producing the next food processor, the 13th one, is $3.38. What's the actual cost? Now, the actual cost would be given by the difference between the cost of 13 versus the cost of 12. So let's use the cost function up here to compute the cost of 13 food processors and subtract the cost of 12 processors. This will be given by the following representation. 13 squared is 169 minus 12, which would be 200, plus 7 divided by 12, plus 144 divided by 7. When you work this one out, you come up with a a value of $3.53, roughly. In other words, the actual cost of the 13th one is $3.53, but our predicted value, the marginal cost, was $3.38, which is pretty close. I hope that this is making sense to you and that you're enjoying learning about the applications of the derivative. We're going to be continuing our discussion of the derivative in the next video, where we'll be taking a look at the derivative of trig functions. We need to add to our repertoire of being able to take the derivative of different types of functions, and we start with the derivative of trig functions. I'll see you in the next video.